Well, how's it going, guys? So this is Mr. Brisky's new chemistry classroom, otherwise known as my study. As you can see, it's a little crowded and a little small, but we'll make do with it as best we can. So in the video you saw before, we learned about Graham's law, and I got quite a few emails from people saying that they were kind of confused about what I had taught or had tried to teach electronically with Graham's law. So let's take a minute and review it. So Graham's law tells us that the rate of diffusion or effusion of a gas, in other words, the ability of a gas to travel, is inversely proportional to the square root of its molar mass. In other words, the rate of gas 1 over the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Now you have to flip them because it's an inverse relationship. So in other words, as the molar weight increases for gas 1, its rate of effusion becomes less. As molar mass decreases, the rate of effusion becomes greater. It's an inverse relationship. Now some of you might find the term rate confusing, so if it's more helpful, you can think of speed. The speed of the gas is inversely proportional to the square root of its molar mass. In other words, like we talked about with kinetic molecular theory, smaller gases move faster, larger gases move slower. Alright, so what I want to do is just kind of go over a couple of the problems and try to show you how you apply Graham's law to these situations. So we're just going to erase this. This is my little makeshift whiteboard. Unfortunately, they have cut off my access to the school because they want to really clean it really well and sanitize it and get rid of any potential coronaviruses or viri that might be in the school. So, if you could please, on your device or on a computer or something like that, if you could follow along with the problems I'm going to do, and when I go to edit this thing, I'm going to try to put the text on the screen. I don't know how well that's going to play out though. So here we go. How much faster does nitrogen diffuse compared to neon? Okay, so we go back, we take Graham's law. So the rate of gas 1 over the rate of gas 2 is equal to the square root of the molar weights. So this is the molar mass of 2, and this is the molar mass of 1. Now let's actually take this and apply it to this problem. So how much faster does nitrogen diffuse compared to neon? Now, there are a number of ways that you can put this in, and it really doesn't matter which numbers you put, insofar as you are consistent. Whatever you call R1, you got to put the molar mass of R1 down here. Whatever you call R2, got to put the molar mass down here. In the problem set, in the answers I emailed everyone, I did it one way. Let's do it the other way. So the rate of nitrogen over the rate of neon equals the square root of 20 divided by 28. That's supposed to be an 8. See, I'm no more neater on this than I am on the whiteboards back at St. Ed's. So 20 over 28, you do the math. You could either square root 20 over square root 28, or take 20 divided by 28 and take the square root of that. Either of those would work. Let me say that one more time a little slower. You could take the square root of 20 and then divide it by the square root of 28. Or you could take 20 and divide by 28 and then take the square root. It really doesn't matter. You'll get the same answer regardless. And so what you get for that first problem is 0.85. That means that nitrogen is 0.85 as fast as neon. Or, if you look at the answers online, I said 1.18 because I flipped it and I had neon on top and nitrogen on bottom. Again, it doesn't matter. It's a question of relationship. So this equation tells me that neon will diffuse or effuse 0.85 as quickly as nitrogen will diffuse or effuse 0.85 as fast as neon. In other words, slower. Or you can express that as 1.18 times neon is nitrogen. In other words, neon effuses or diffuses 1.18 times as fast as nitrogen. So that's how you do the first one. Let's take a look now at number 3. What is the ratio of effusion rates for krypton and neon at the same temperature and pressure? So once again, this is going to be a Graham's law problem. And we assign one of the gases as R1 and the other one as R2. It doesn't matter which one as long as you are consistent, like I'm saying, with the molar weights. So, we have the rate, of neon, we have the rate of krypton. Not to be confused with kryptonite. Equals the square root. Now remember, neon needs to go on bottom, krypton needs to go on top. Where do I get these molar weights? Well, I wonder. Maybe this table that Mendeleev developed that we talked about last semester, hint, hint. Obviously you get these from the periodic table. So, we're going to take the molar weight of krypton, which is 84, divided by the molar weight of neon, which is 20. And this will lead us to the answer of 2.05. 2.05. Forgive my little whiteboard of science. If we have online school or whatever 2 weeks from now after spring break, I will try to think of other things we can do to try to deliver content. But this is what I got for right now. So, neon effuses 2.05 times quicker than krypton. That's what that means. That's the meaning in like plain English or whatever. Okay, so let's do one more. And you know what? Let's do two more to try to explain how this works. And then I'm going to give you guys another problem set, and I hope it's a lot more successful. So let's erase this guy. Just going to take this moment to say I totally miss all of you. And I'm looking forward to the day where we can come back together and be a class again. Because this is a lot less fun than teaching you guys in person. But it is what it is. We gotta, what do they call it? Lengthen the curve, or spread the curve. Widen the curve. Okay, so let's look at number 5. Calculate the molar mass of a gas that diffuses 3 times faster than oxygen under similar conditions. Now, in this time, we're not told what this gas is. We're told that it diffuses 3 times faster than oxygen. Okay? So, there are 2 ways you could set this up. You could make R1 the unknown gas, or you can make R2 the unknown gas. What we do know is that it's 3 times faster than oxygen. So, let's make this ratio 3. So, just as a reminder right now, I am on number 5. We make the ratio 3. So 3 is equal to the square root of, so 3 is on top, so it's a 3 over 1, if you think of it that way. So 3 is the unknown gas, 1 is the known gas, 1 is oxygen. So the molar weight of oxygen is O2, its molar weight is 32, divided by X. Alright, so now we're going to solve for X, the molar weight of the unknown gas. Let me make this square root a little better to make more sense. So, easiest way to solve this, square both sides. We square both sides, the 3 becomes a 9. And the square root sign disappears. So now we're left with 9 equals 32 over X. And now, simplest thing to do, play flip them. This is a weird way to teach. Make this an X, and there you go. So 32 over 9, or 3.55. So the molar weight of the unknown gas was 3.55. And there you go. That's the answer to number 5. So, let's do one more. Let's take a look at number 7. Alright? So we're going to erase this guy. And do number 7. An unknown gas diffuses 1.62 times slower than does oxygen gas. Calculate the molecular mass of the unknown gas and predict what the unknown gas is. Alright, so you got to look at the language closely. It diffuses 1/3 times as fast as oxygen. Alright, in other words, oxygen diffuses 3 times faster. So you could put it as 1 over 3 or you could put it as 3 over 1. It doesn't matter insofar as you are consistent. All right, let's make it 3 over 1. So if this unknown gas fuses a third as fast as oxygen, another way to word that is that oxygen is 3 times faster. So let's make oxygen 3 times faster. That means 3 over 1 equals radical. Now, MM2 is going to be my unknown, because that's this one, over the molar weight of oxygen, which is 32. All right? The 3 is oxygen here. The 32 is oxygen here. They are inversely proportional, like we talked about. Now, same deal as before. You solve for M. In the notes online, I said you multiply both sides by radical 32. You could also square both sides. In the end, you get MM2 is equal to I gotta check my notes. MM2 is equal to something, isn't it? 84. Alright, so MM2 is krypton. Kr, that's the unknown element. So we've reviewed how to use Graham's law. The idea is that the ratio of the rates, or the ratio of the speeds, is inversely proportional to the molar masses. So whatever you call R1, you have to make the molar mass of that on the bottom. Whatever you call R2, you have to make the molar mass of that on top. And how do I get the rates? Well, the problem will tell you that. The problem will either say something is 3 times faster or 4 times faster, or it'll say this gas has an diffusion rate of 0.45 moles per second. The problem will always give you some way to solve it. You just have to read it carefully and figure out what they're trying to ask. And as always, if you have questions, shoot me an email. This is Mr. Brisky with St. Ed's Chem signing off. Hope you guys have enjoyed this little lecture coming from my study. And I hope that this coronavirus thing ends soon so I can see you all after spring break. Goodbye for now.